So the next section we have is one of my favorite projects, it's PyIceberg. We have Hana, who's also who's also one of the PVC members, walking us through Hana with Snowflake. Is that right? Yeah. We have a break after this, after 20 minutes. So yeah, immediately after this time.
Maybe not in. Probably not in. I know.
Hi everyone. I'm going to get started. So I'm Jonas, a software engineer from Snowflake, and you may also know me as Honor in the Iceberg community. I'm also a PMC member of the Apache Iceberg. And today I'm going to give you an introduction talk of the PyIceberg, which is the Python implementation of Iceberg. So I will do a very quick overview of the Iceberg's metadata structure. So on the right-hand side is a very wonderful picture showing the core structure of the Iceberg. Starting at the bottom, we have the data files as Avro, Parquet, or org, and they are grouped into manifests. And manifests are then grouped into manifest lists to form snapshot of the table. The snapshot are then grouped and recorded in the metadata file along with other metadata such as schema, partition spec, and table properties. And each metadata represents one version of the table, and Iceberg use a catalog server to keep track of the latest metadata location of each table. And Iceberg won't be so popular without a way to allow users to easily interact with it. The reference implementation was first written in Java and later expanded to Python, Rust, C++, and Go. For the Python implementation, our goal is to bring the value of the Python to make the overall interaction much simpler and more lightweighted. So PyIceberg brings a pure Python package that allows you to do this. It contains a library of Iceberg APIs. It is also served as a lightweighted engine that allows you to make queries on its tables. It can also serve as a client tool to allow you to grab some information from your catalog, namespace, and table when you run it as a command line. To work with different platforms, PyIceberg supports various catalog services and storages. For example, for catalog, it supports Glue, DynamoDB, Hive, and SQL, and also all the catalogs that implement the Iceberg REST catalog OpenAPI stack. For the storage, it supports famous ADLS, ECS, S3, and HDFS. And PyIceberg also supports all the essential Iceberg features like hidden partitioning, schema evolution, partition evolution, time travel, and transactions. PyIceberg also serves as connectors to other libraries, like the famous pandas, Pyro, Ray, DuckDB, and Dust. And for example, you can convert your query result to a pandas data frame with just one line code, and we will see that later. Oh, and final part, how to install it, it's very simple. Since it's a Python package, you just pip install it. And if we also provide some optional dependencies, and you can specify that when you are doing pip install. Now we will take a deep look at PyIceberg by going through a demo. In the demo, we will create an Iceberg table using PyIceberg, make it partitioned, and add some data to that. And later, we will explore what actually happens in the background when we add data to the table. So for the demo, we will use a very simple example data. You can see on the left, it's a 3-column example data set of name, ID, and date. And on the right-hand side, we will use the PyIro to represent this example data set as an in-memory data frame-like object. So we first define the schema of this PyIro object, and then we convert that into a PyIro table. And before we create the table, we also have to define a catalog that allows us to actually call the create table API and do the table updates later. So in this example, I defined a REST catalog connecting to a server powered by Apache Polaris. And I won't go into details about how to set up the rest, but basically you just give it the URI of the server and give it the credential. Creating a table is very simple. The first thing you need to do is to create a namespace that holds the table, and then you will call the create table API by giving it the name of the table and also the table schema. You may notice that here I directly pass in the arrow schema, which I just defined. This is a convenient feature of PyIceberg that it can allow you to directly use the arrow schema to create the table instead of take a further step to converting it to the Iceberg native schema. And so the table is created, and let's take a look at what's inside it. We can use PyIceberg's spy tool describe to see what's inside the table. And we can see here the table contains some metadata, and the schema is expected. The partition spec is now empty, meaning that table is unpartitioned. But let's make it partitioned. So in this demo, we will try to partition by the date column. But we don't want to partition by the raw date. We want to partition by the year part of the date. PyIceberg supports the hidden partitioning, so you can rely on the built-in year transform to extract the year part of the date. Below, I give you the code example that can easily do that. You first have to initiate an update partition spec transaction, and you add a field by giving it the name of the column and the year transform. And now we're ready to add data to it. Remember, I created an arrow table that holds the example data. And all you have to do is to call the append method and give it the arrow table. And PyIceberg will handle the rest of the thing for you. After we append the data to the table, and if we use the same flight tools to inspect the table again, we will find that now the table contains one snapshot, and the snapshot pointing to its corresponding manifest list file. And inside the manifest list, we will see at the bottom, we have one manifest and containing 3 data files. Each of the data files will be resides in their own partition. So what actually happens when we add data to the Iceberg table? The first step PyIceberg will do is to generate data files. PyIceberg will first take the input PyIceberg table and split them into chunks. The chunks is also known as the record batches in PyIceberg. And rows will be grouped by their partition key in these batches, meaning that each record batch will contain rows from the same partition. And large record batches will also be separated into different pieces so that each of the record batch will finally match our target file size. And then Iceberg will use PyIceberg's packet writer to turn this record batch into packet files. And at the same time, we will collect the statistics, such as null counts, record size, min, max. And the stats combined with the Parquet data file will form a list of the new data files. Once we have the new data files, the next step is to generate manifests and the snapshot. In PyIceberg, by default, the strategy we use to append is called fast append, meaning that the snapshot producer will always create a new manifest to hold the new data files, instead of adding those new data files to some of the existing manifests. And after we have the new manifest file, we will combine that with the existing manifest file to form a new manifest list. So the new manifest list will be the new snapshot. And we have one more step to do is to add the new snapshot to the table metadata. PyIceberg updates the table metadata by taking the formalized table updates. And here at the bottom, I specify the 2 updates that we will use in this case. The first is the add snapshot update, which registers the snapshot to the metadata snapshot list. And second is the set snapshot reference update, which tells the metadata to change its current snapshot pointer pointed to the new snapshot we just added to it. And once we have these table updates, we can parse it to the catalog to update the table. So the catalog will generate the metadata file and change the table's latest metadata location. So here is a flowchart for that. Once you have all the updates, the PyIceberg will parse that to the catalog's commit table API. And if you're using non-REST catalog, PyIceberg will first verify all the requirements and apply updates to generate a new data file. And then it will atomically update the table's current metadata location pointing to the new metadata file. If you're using REST catalog, PyIceberg will just serialize and send all the updates to the server, and the server will handle the rest updates. So now we have a table with example data in it. And the next question would be, how can we read it? It's also very straightforward. So in PyIceberg, first, you will have to create a table scan by the table.scan. And then from this point, you can convert it to an arrow table by calling toArrow, or you can convert it to pandas by calling toPandas. Depends on what you need. And in most of the time, you will also find it necessary to apply some filters when reading the table. So PyIceberg can allow you to write your filters like when you write the while clause in the SQL. For example, here, I can write name equals to Alice, or the date equals to 2022, July 1st. And the PyIceberg will parse these into the Boolean expressions and apply that when scanning the table. And you can also choose which columns to appear in your query result, and you can also limit the total number of columns in the result. Beyond the basic read and write of the Iceberg table, PyIceberg also supports more table updates, such as schema evolution, partition evolution, and we will went over them one by one. So the first is schema evolution. PyIceberg will allow you to update the table schema in a very easy way. On the right-hand side, you will see the example. But first, you will have to initiate an update schema transaction. And within the transaction, you can add new columns to the table. You can rename or delete an existing column. And you can also change the column type, the column data type, following the promotion rules of the Iceberg. So for example, here you can promote column type from the integer to long. Similarly, you can update the table's partition by the update select transaction. Within the transaction, you can add new partition field, you can remove partition field, and you can rename it. But please note, these are all metadata-only operations, meaning that the existing data will not be rewritten. Only the new data that added later will follow the new partition strategy. And PyIceberg also allows you to group all these updates into one big transaction. By initiating a transaction by table.transaction, and you can do all the updates we just went over before in a one transaction, and they will be grouped and committed as a whole, meaning that if any exception or error occurs in any of these updates, the whole transaction will be aborted. And finally, PyIceberg also supports a time travel query, which allows you to read the table at some certain point in the past. For example, at the top, I first append dataset 1 to the table, and I record the timestamp. And then I append another dataset to the table. Now, how do I query the table at a time while the second dataset hasn't been added to the table? Since I record the timestamp, I can use the snapshot as a timestamp method to get the snapshot at that point. And I can further fetch the snapshot ID from that snapshot and give it to the table scan. And so in this way, the table scan will be performed on the table at the previous point, not the current one. So that will wrap up all the features and examples I would like to share today. So just a summary, we go over how to create a table, we go over how to add data to the table, and we went over a little bit of how things happen, how data are actually created and added in PyIceberg. And we also go over how do we update the table, the schema evolution, the partition evolution. For more details, I would recommend everyone to check out the PyIceberg's website and our GitHub page for more information and tutorials. And finally, I would like to give a big thanks to all the contributors in the PyIceberg community. It is their great effort that make all these wonderful features possible. And thank you so much.
Yeah, we have time for a few questions. So, does anybody have any questions?
Is the PyIceberg is on top of it's a client to the Java client, or how does it work under the hood?
Sorry, you mean?
So PyIceberg is out does it talk to the JVM client to do all the operations, or it's just
You mean is it on a Java client or something? Oh no, it is not. It is a purely Python package. It can work without a JVM. And in the future, we are currently introducing the Iceberg Rust core powered by the Iceberg Rust repo, so that we can accelerate some of the internal process for the Iceberg. But we won't introduce any Java client or JVM in Iceberg in the future. Yeah, it's pretty slow. It's not possible.
How's the performance against, write performance, versus using Spark or something?
So I would say, right now, the actual write performance is not so good in comparison with Spark. So, and also, another bigger issue than the performance is the scalability. So it's also we have the scalability limit here. So that's why we're looking into pushing some low-level logic to the Rust so that we can have more power on that. But let me add that. So PyIceberg is pretty good at metadata managing. So if you, yeah.
Okay, just wondering about this question. So when you run the PyIceberg, so is the default just only using one node? If you have a created EMR cluster, say 40 nodes, can you run PyIceberg using all nodes, do a parallel distribution?
So right now, PyIceberg is a single noded application. We cannot support in the distributed environment, and that is also a part that we will be working on.
Basically, the PyIceberg just kind of benchmark testing purpose.
Yeah, it's also if you want to do some for example, if you just want to modify a property of the table, you probably don't want to start a Spark cluster in your computer, right?
Yes.
Yeah, so with some of the consumer box, like a Mac Studio Ultra with 20 CPU cores, what's the plan of PyIceberg to actually leverage that 20 CPU cores?
Well, so right now this is I would say a to-do thing. Python is well known as limited by its global thread locker thing, but it's unlocked in Python it's a 13 version. But we haven't finished the actual update to leverage that features, but we will do that in the future.
Any other questions? Cool. Sorry. One last one, and we'll take a break.
All right, thanks. So, if we were to deploy something like this to production right now, is there some world where you have Spark do the right jobs and then PyIceberg just do the metadata management or something?
So I will give you an example that it can be used in production. So let's say, right now the pain point is that when you ask PyIceberg to actually write or generate data files, it's very slow. But let's say if you already have Parquet files generated, we also have an API that called add files that you can directly add existing Parquet files to the table, and that will be very fast. or at least very fast compared to the actual like write operation of PyIceberg. And that is like that will give you like a lightweight solution if you already have some other procedure that generated those data files and you just want to add that to your existing Iceberg table. Thanks.
So, quick thing, what is the future of PyIceberg, or what are the, where do you see that going?
So I would say like, so I would say that there are two parts. The first part is that we will keep trying to catch up on the feature gap with the main Java repo. So for example, right now we have still have some poor support on the equality deletes. Well, actually, we don't have support for that. We support positional delete, but it's only on the read side, not write side. So these are the things we need to catch up on. But we are doing. So right now we are doing a lot of work in pushing the V3 support in the PyIceberg. So that's the feature part. And for the project part, I guess we will keep making it work in the distributed environment and to make it more like an engine, or at least allow you to make some complex queries and make it more scalable and distributed. And another aspect is that if we'll also consider to organize APIs before we claim the 1.0 release. So that will also help if other actual Rust or Python engine who just want to rely on PyIceberg to do some of the metadata logic while keeping the actual engine side job in its own. So we will also do that. This is on the way. We currently allow you to create a branch. It's not there yet. Yeah, but it will be.
Thanks a lot. We're going to take the dinner break now up until 6:30. So we'll be starting the sessions again. We've got 3 more exciting sessions planned. The dinner is being served right outside as soon as you walk out of the door. We'll be coming here back at 6:30. Thank you.